I am very happy to present Tim Lichtenberg from the University of Oxford. He actually did his PhD in Federal Institute of Technology in Zurich, and he had done his diploma studies before in Germany. Now he's at the University of Oxford in the UK, and I will now leave the floor to him. Many thanks for coming, Tim, and go ahead. The floor is yours.
Yeah, thank you so much. Let me try actually if I can my screen sharing again. Yeah.
So up to now we had only problems once.
All right, do you see my screen and do you see my mouse?
Yeah, it seems to work.
All right, thank you so much. Yeah, thank you everyone for showing up despite the irregular schedule today. Yeah, and thank you, of course, for the EAI team involved for inviting me and giving me the chance to present the research of me and my collaborators today. So what I will do today is speak about, so in general, I work at the interface between astronomy and geosciences. And my research goal in principle is to understand the origin of habitable environments with a specific application of how volatiles are processed during planetary formation and how planetary bodies evolve geophysically both during the accretion process and then cool and solidify and form either habitable environments or the opposite of that. And that ultimately, this understanding of general planetary physical and chemical principles feeds onto our understanding of the planetary context of the origins of life, both on Earth and potentially on habitable exoplanets. And today specifically, I want to talk about how the earliest geophysical evolution of planetary bodies, both in the solar system and in exoplanetary systems, can create divergence in potentially climate regimes at both volatile abundances and how these can be measured with current and near future exoplanet surveys. So the key theme of the talk is distinctions between the solar system and architectures or planetary regimes in exoplanetary systems. And in order to initiate that, actually I want to show first here the architecture that you know all very well, the solar system. Until about 25 years ago, the only planetary system, of course, that we knew. And in that historical context, I think it's really, highly relevant to, just shortly look at this peculiar architecture again, which is, these 4 terrestrial planets, small and dry, and separated by an asteroid belt from more massive, very volatile rich planets. And so until the exoplanet revolution, really this system that we have come to accept as the norm, at least where we live now, and the place in the universe where we live, was really the only one that we knew. And all our theories and all our understanding was sort of primed to recreate this architecture and these chemical compositions and atmospheres that we observe in the solar system. All of that changed naturally in the last few decades, and now we can study these general principles, physical and chemical principles, in a much wider range of scenarios. And that, of course, showed us that the solar system architecture and the chemical budgets of the terrestrial planets, for instance, are not the only possible way, and there are multiple and myriads of other potential outcomes of the planet formation and evolution process. So to illustrate actually the stark differences that we can observe, I shortly want to go through this mass radius diagram of observed exoplanets. So this is a few years old, this diagram, but generally it still displays very nicely the differences or the points I want to make here. And actually this important regime here at the bottom left hasn't filled up much further since then. So what you see is planetary radius and Earth radii, planetary mass and Earth masses. And the Earth is somewhere down here. And the dots you see are known exoplanets with uncertainties, color-coded with equilibrium temperatures. And the isolines here show lines of fixed composition. So for instance, if your planet is somewhere up here, then this means the planet is generally more Jupiter-like, full of hydrogen and helium or other volatile species, like this, for instance. If you are down here, then the planet is composed more of denser elements, mercury, metal, rock-like. And if you are somewhere here, then at least theoretically, it is possible that the subclass of planets may harbor very water-rich components, something approaching very large tens of weight percent water mass fractions. So intuitively, you think, of course, this is unlikely, but we know these planetary objects from the solar system. Ganymede, for instance, is something like this, and the outer solar system objects all generally tend to have very volatile rich compositions. So we may also see something like this in a more planetary regime that we are usually used, where we're usually used to seeing more rocky compositions from our everyday experience on Earth. Now, this brings up the question, really, what is the Earth-like mixture? You know, what are the boundaries of this regime down here to the left, when we can call a planet really still an Earth-like planet, and compare it to our everyday experience on our own world? Now, to illustrate how complicated it or complex it is in the light of the uncertainties that we have with exoplanet surveys, you see here these massive uncertainties for many of those planets. So this diagram here illustrates the difference between an Earth-like world and an icy world. So the right-hand side shows an Earth-like world with about 0.1 weight percent of water in its interior, like the Earth. This enables a liquid or shallow liquid water surface in principle, where continents essentially can stick out. If instead you just add 1 weight percent, in cosmochemical abundance, this is not a lot. If you would just add 1 weight percent of water to the Earth, then instead of having a surface like we observe it today, then this whole planet would be covered in a global ocean. And because of the equation of state of water, actually at the base of this global ocean, the water would instead be a high pressure ice form. And that means that any geochemical cycling between the mantle, the interior of the planet, and the atmosphere would be inhibited. And for instance, cycles or the temperature buffering, like we observe it on Earth, would be inhibited. Now, this still seems very theoretical so far, but actually we have some evidence for these objects out there. The famous TRAPPIST-1 system, is shown on the left-hand side, gives some evidence, even though this is debated, of course, like all things exoplanets, gives evidence that the outermost planets are in fact ice worlds like the one here illustrated on the right-hand side. So what you see is that these are periods and days and semi-major axis of the TRAPPIST-1 planets. This is water mass fraction. And these dots here are the TRAPPIST-1 planets for various guessed values of the iron mass fraction. So if we assume, for instance, an iron mass fraction of these planets of about 32 weight percent, which is the Earth-like value, then you see that these planets here in the outskirts of the system are all very water-rich, with tens of weight percent of water in the interiors, putting them firmly in this regime. Okay, so this suggests that maybe the formation environment may produce strong or variable both mass budgets of exoplanets just in general. And so we need to, you know, understand and survey the range of planetary regimes in a much wider, we need to cast a wider net relative to the solar system terrestrial planets. Now, from a formation perspective, the last few years actually have seen tremendous advances in our understanding of the planetary formation process in general. And there are two very specific lines of evidence that I want to highlight here specifically. One is that we have now abundant evidence for temporal fragmentation of the planet formation process. And the first one is that planets form extremely early. They form contemporaneously with their stars. Not later, but they start together with the protostar. They start their formation when their own star forms at the same time. You can see this. We have evidence about this from exoplanetary systems and from the solar system. The left-hand side shows this evidence from exoplanetary systems that we have. The y-axis here shows mass in solids, in disks or exoplanets. And the x-axis, the stellar mass, is not very important for the argument I want to make here. Now, the lines, red, blue, and this yellowish, greenish, show the mass that is observed with the Atacama Large Millimeter Array in these disks, integrated over star-forming regions from class 0, class 1, class 2. And class 0 and 1 disks are when the protostars and planetary systems are still in their formation phase and the star is still actively accreting material from the surrounding environment, while the class 2 disk stage is in a calmer environment when it's disconnected from its formation environment. And what you can see is that in this class 2 stage, the mass here is below all these dots. These are the exoplanet masses that we observe. And this is super weird, right? Because it suggests that actually class 2 disks are not massive enough anymore to form the exoplanets we observe, immediately suggesting that exoplanets actually must form or start forming in the class 0 and class 1 stage to explain the masses we see. We have corroborating evidence from the solar system for this trend. This is shown here on the right-hand side. Let's focus on this B part of the diagram here. The x-axis shows time after CAI formation, where CAIs are the oldest known solids that we know in the solar system. This is in millions of years after their formation, which is typically taken as the time of solar system formation. And for the argument I want to make, only the x-axis here is important, actually. So what you see is these dots, these various dots, and these are various classes of meteorites in the solar system. For instance, iron meteorites, magmatic iron meteorites mostly, achondritic bodies that melted, and chondrites, which have chondrules and are relatively pristine. And what you can see is that, especially in the inner solar system, which is the red parts here, I'll come to this color coding later on, the onset of planetary accretion is within the first million years after CAI formation, firmly starting within the class 1 phase of the solar system. Okay, so this seems to suggest that the planetary accretion process starts rapidly together with the solar system or with a protostar. But we have not only this evidence, from the solar system at least, we have evidence for an early onset, but a protracted finish of the accretion process. And this is shown here. This diagram here collects various evidence from geochemistry, mostly for the solar system planetary objects, mainly the moon, the Earth, and Mars, for which we have a lot of evidence from meteoritics and geochemistry. This suggests specifically for the Earth that the final accretion stages took until about 50 to 115 million years after the start of the solar system. So you have a rapid start, but a protracted finish of the accretion process. Additionally, in addition to this temporal evidence for temporal fragmentation, we have evidence for spatial fragmentation. And most of you have probably seen this. There's a lot of discussion surrounding the various rings and gaps and the structures in ALMA disks that you can see here on the left-hand side. So this is structure formation in the solid component of these disks, which is, of course, debated what is the origins of this. Some argue for planets, others argue for various ice lines or heterogeneities in the disk. So it's unclear and probably varies from disk to disk. Now, irrespective of what the cause of these rings and gaps is here, we have again corroborating evidence of spatial fragmentation of the planet formation process from the solar system. And this is illustrated, or often called in the community, the isotopic nucleosynthetic isotope dichotomy. What it basically is a shift in stable isotopes between planetary bodies, more from the inner and more from the outer solar system. This is illustrated in this plot here. This basically plots deviations in chromium-54 abundances versus titanium-50 abundances relative to the Earth. So the Earth sits here, the Earth upper mantle sits here at 0, and you see that every other object in the solar system, like meteorites and planetary bodies, they are shifted relative to the Earth. But they cluster in two large supergroups, the non-carbonaceous reservoir, or the NC reservoir, and the carbonaceous reservoir, the CC reservoir. Okay, this seems to be interesting. And what it tells us, actually, I want to add this deviation here tells us that the solar system itself, the matter that formed the sun in all the planets, formed in at least 2 nucleosynthesis events, such as a supernova with Rayet stars or neutron star mergers, for instance. At least 2, probably many more, but at least 2. Okay, So this seems interesting, and so it suggests basically there's some order to the chaos, and immediately brings up the question if this isotope dichotomy that we see is somehow connected to the chemical deviation that we observe in the solar system that I started with. A dry and small inner solar system, low mass inner solar system, and a very wet and high mass outer solar system. Coming back to this, the Earth, even though there's a lot of water on the surface, is actually very dry, while outer solar system planetary bodies like Europa or Titan or Ganymede have a very large water mass fraction. So very classically, of course, the idea for this is that there's, during planetary formation, the disk, there's a sort of snow line or frost line, where inside of which all the water is in vapor form, and outside of which all the water is actually solid, in solid ices. Okay, this is interesting, but we have now all this additional evidence that basically tells us about a fragmentation in time and space of the planet formation process. So it's not directly clear anymore that the picture is that simple, because we have really a detailed chronology of on a 100,000 year time scale during the circumstellar disk phase. And this is important since planet formation actually really is a long journey. There are multiple steps that can go wrong on that journey, while grains start coagulating, growing until they become fully fledged planets. And specifically in the last 15 years, I would say, the community has invested a lot of time into understanding various growth barriers on that journey. So these plots here illustrate some of them. For instance, the bouncing fragmentation barrier that prevent grains from coagulating basically beyond millimeter sizes to sort of meter sizes, and the radial drift barrier, which makes grains radially drifting toward their protostar because they feel an ambient and headwind, a sort of headwind from the ambient disk gas, and which makes them lose angular momentum and stream toward the protostar. Okay, so these growth barriers in principle are a problem theoretically because they are so effective actually that grains shouldn't coagulate further in principle from millimeter to meter sizes. And so planets shouldn't form in general theoretically, but they do. We know that. We see exoplanets, we are here, we're standing on a planet, so somehow it must work. And the community consensus, at least from the past few years, seems to indicate that actually a likely solution to this problem is a process called the streaming instability, which is a fluid dynamical instability where large amounts of dust mass gather together in isolated regions where the dust mass can be locally enhanced. And this dust mass is so massive that actually the grains coagulate directly. They do not coagulate. They gravitationally collapse directly and go from millimeter sizes to kilometer sizes, basically jumping over the centimeter-meter barrier. So if this mechanism works, like it's illustrated here in that right-hand side video, to directly form kilometer or 100 kilometer sized planetesimals actually from millimeter sized dust grains, this changes the question to how does the planet formation process nucleate, to how can we enhance the dust to gas ratio from an astrophysical point of view. Now, this is an interesting aspect because it directly connects with the first slide that I showed. This showed the structure of the solar system, right? Where there are planets everywhere, but there's a clear mass and chemical dichotomy in between them. So since basically forever, since tens of years, the snow line itself has been debated as a very prime location for enhancing the dust surface density in the disk because of various effects surrounding water vapor that go on at this stage. Now, with the enhanced picture of dust redistribution coagulation of the disk, that brings two specific mechanisms into focus that locally enhance the dust density at the snow line and make it the prime location actually for local planetesimal formation. Not disk-wide, but local. There are two effects operating. One is called the traffic jam effect and one is called the cold finger effect. How does the traffic jam effect work? So generally, outside of the snow line, water is in the ice phase, and inside it's in the vapor phase. Now, if these dust grains here that basically can grow to larger sizes because ice is more sticky than non-ice rich grains, they will start to drift inward because they lose angular momentum from the ambient headwind. and they will drift inside and then evaporate or sublimate. The ice component will sublimate at the location of the snow line. And that means grains just inside of the snow line drift a little bit less fast or slower than these grains outside. And this leads to a sort of traffic jam effect that locally enhances the solid mass or the dust surface density at the location of the snow line. And this triggers the streaming instability locally and can form a lot of planetesimals. Now this works on a time scale of about 10 to the 5 years, which is approximately the coagulation redistribution time scale on disk-wide scales from the outer solar system or from outer planetary systems. There's an additional effect, though, that is important in the context of what I will say next. And this is the so-called cold finger effect. And this effect is much, much faster. It works on a 10 to the 3-year time scale, but it's less effective. So how this works is by dust diffusion. So you have water vapor inside the disk that diffuses outward and very temporally enhances the dust surface density by refreezing of this water vapor onto grains just outside of the snow line. And this again can trigger the streaming instability by enhancing locally the dust surface density. So why is it important? Why do I explain this in so great detail? The reason is we want to explain the solar system in the context of exoplanetary systems, right? And we have these additional lines of evidence that suggest very rapid planetesimal formation that is hard to achieve actually in classical models of planetary formation. So we did this 1 year ago and tried to understand how the solar system structure and chemical budget can be formed in a model that accounts directly also for the accretion of the protostar itself. So in this model, basically, this goes back to the inside-out rotating inflow models from Shu in the 1970s. Basically, it is assumed that there's a giant molecular cloud core that has a given angular momentum, and then it collapses and forms the disk from the class 0 to the class 1 stage from the inside out because of angular momentum conservation of the disk. What happens then is shown in this video here. So what you will see now is a video that basically calculates planetesimal formation over time and orbital distance during the transition from the class 1 to the class 2 stage. And this has been work done, published in Ronchkos and Gilman in 2018. So this here is orbital distance, this is time in millions of years, and this is the surface density. And you see the movement of the snow line from the class 1 stage to the class 2 stage. It moves outside and then it moves inside again. The reason here is that during the class 1 stage, the disk is viscously heated, partly because of the gravitational potential energy and partly because of the viscous heating itself in the disk. And then in the class 2 stage, the temperature structure of the disk changes and it can cool because the main heating mechanism at this stage is irradiation alone. Now, as you can see, there are two red blobs, and this here in this specific illustration means a change in the planetesimal formation rate. So there are two local bursts of planetesimal formation operating because of these mechanisms at the snow line that I explained to you on the past few slides. The first burst of planetesimal formation here is triggered rapidly by the cold finger effect on a time scale of 10 to the 3 years, and ultimately leads to planetesimal formation on the time scale of the class 1 phase, so within the first few 100,000 years after solar system formation. And the second burst is triggered by the so-called traffic jam effect, and operates much longer and enhances the solid surface density by much more, and can trigger many more planetesimals extended over an extended time scale and over an extended area while the snow line moves continuously inward. You will see this basically now from now on in color-coded in this illustration here in orbital distance, time, where in the first reservoir, let's call it reservoir 1, and the outer reservoir in blue, let's call it reservoir 2. Okay, so coming back to this plot here, now with the helpful color choices for the non-carbonaceous reservoir in red and the carbonaceous reservoir in blue. So the question is, can this formation scenario explain the isotropic dichotomy that we see in inner and outer solar system objects? So the question here becomes, can this structure formation or planetesimal formation mechanism that initiates ultimately the growth of planets, can this prevent complete homogenization of the disk. And this is actually the central question of the isotope dichotomy. This plot here, from an astrophysical point of view, shouldn't exist, because if you start the disk with initial heterogeneity and stable isotope content, dust grain drift and coagulation and redistribution processes operate on a much faster timescale, on the timescale of drift, which is 10 to the 3 years, on the order of that. So any isotope heterogeneity that is there from the beginning, in the class 2 state, it should be very rapidly homogenized through the entire disk. So consider, for instance, this pebble here has let's say it has an isotope content of X, and then it drifts, and so it basically brings its isotope content to the inside. And this process should very rapidly homogenize the disk. So we asked the question, in this specific formation scenario of the solar system, can this be prevented to some extent? And for that, we basically measured the pebble flux locally at 2 AU and 15 AU and compared these pebble fluxes relative to each other. This is what you can see here on the right-hand side. This again shows time after EAI formation. This is the pebble flux in Earth masses per millions of years. Red is at 2 AU, blue is at 15 AU here on the left-hand side. What you can see is that during the first about 700,000 years, which is in this specific model, the length of the class 1 stage, the pebble fluxes at 2 and 15 AU are roughly comparable. And this means that basically the entire dust mass is dropped onto the disk, and then the disk can homogenize in that time frame. However, after a while, specifically in the class 2 stage, between 1 and 3 mega years, which is roughly the lifetime of the inner disk, the two fluxes deviate strongly. They diverge actually up to 2 orders of magnitude over time. This is very important in that context because it means that a pebble during later stages that starts in the outer solar system is stopped in reservoir 2 and doesn't make it into the inner solar system, giving a physical explanation for why we would see today this isotope dichotomy, because the isotope content in the disk is actually not homogenized. The reason here is that pebbles from the very far outer solar system do not contribute to the inner solar system because they contribute to planetesimals that are formed here in reservoir 2 due to the traffic jam effect over million year timescales. So this is a qualitative summary of that. Basically, the disk starts small, the infall is initially enriched in supernova-derived isotopes, and then it transitions to depleted while the disk basically starts forming from the inside out. At the same time, the snow line moves outward and then experiences sort of tech at the transition from the class 1 to the class 2 stage. And then on these timescales, the dust grains with the isotope content start drifting inward again, but because of that planetesimal formation triggering at the snow line over time, the end result is that basically the outer disk retains an isotope information content that we identify today as CC, and the inner disk as something that we call today the NC reservoir. Now, this is not only about isotopes, and there's a substantial information also about potential shift in growth regimes of the terrestrial planets. So if you follow the discussion in the astrophysical literature over the last few years, there's basically a debate or a shift in the community that discusses the main growth channel. So the more classical regime of planetary growth is planetesimal accretion, which has been basically dominant, or the thought of dominant mechanism of planetary accretion since the Apollo missions. This channel of planetary growth starts with planetesimals of a given defined size, and then these just agglomerate by mutual collisions to form larger embryos and then ultimately planets. The alternative end member regime of planetary growth in this view here would be pebble accretion, where actually the growth is not by mutual planetesimal collisions, but by direct dust coagulation onto already formed protoplanets. So consider, for instance, that protoplanet here in the middle. This is a planetesimal, and this is a millimeter-sized pebble of the disk, a coagulated dust grain essentially. And then if the planetesimal doesn't directly hit the protoplanet, so this is a ballistic accretion mode, essentially you need to hit the cross section of the other body. If the planetesimal doesn't hit the protoplanet, it just gets scattered and vanishes again into the disk and doesn't accrete. The pebble, however, feels the ambient headwind in the envelope, in the Hill sphere of the protoplanet itself, and basically continuously loses angular momentum and ultimately spirals inward and coagulates onto the protoplanet. And therefore, in certain mass regimes and in certain disk regimes, pebble accretion can be much faster than planetesimal accretion. It's not efficient, it's very inefficient actually, but it can be rapid. Now, we asked the question specifically with regards to the terrestrial planets, what would be the main growth channel in that disk build-up scenario that can also explain the isotope dichotomy? And this is explained here at the bottom right, which shows the growth timescales in millions of years, again against time after CEI formation. For simplicity, let's just focus on the red lines here. So the solid line here shows pebble accretion, so the efficiency of pebble accretion, or better the growth timescale, which is the inverse of efficiency, versus planetesimals. And you see that in the beginning, during the class 1 stage, the growth by planetesimals is much more efficient than by pebbles. So the growth timescale is smaller for planetesimals than for pebbles. And that is because during the class 1 stage, there just are no pebbles around, because the coagulation and drift timescales are longer than the actual build-up timescale of the disk. And therefore, the initial growth phase of the terrestrial planets in the inner solar system was by mutual collisions, by planetesimal accretion, until they reached larger sizes during the class 2 stage. And then here, in between about 1 to 2 mega years after CEIs, the growth phase actually switched, because at this point in time, if you look here, or better actually look here, between 1 and 2 mega years, the pebbles from the outer solar system could still enter the inner solar system. And only then the outer solar system started really building up planetesimals, and the pebble flux here switched completely. And at this stage, the growth mode again switched, because pebbles from the outer solar system, from here basically streaming inside, they couldn't enter the inner solar system anymore, because the traffic jam effect at the snow line was so effective that pebbles were basically blocked from entering the inner solar system. Qualitatively, this is illustrated here. So again, in the very beginning, the disk was small, there were no planetesimals, but then the first wave of planetesimal formation was triggered in the inner solar system, outside of the snow line. That led to icy planetesimal formation, then collisional growth, and then pebble accretion, a little bit of migration. And the same happened in the outer solar system, but with a later onset and with a faster overall succession of these initial growth stages, because the pebble flux was much higher in the outer disk. And this brings us back to this water question. Now, you may have spotted the problem here, right? Every planetesimal in this formation scenario is formed beyond the snow line. This is weird, because I said it started in the beginning. The Earth is actually dry. This brings us back to this geophysical evolution of planetary bodies, because it turns out that from geochemical evidence, we know that the initial growth phase of the terrestrial planets, actually, the very early formed planetesimals, were dominated by the decay heating of aluminum-26. Later phases were accretion energy dominated, basically the gravitational potential energy of accretion. But the early phases were dominated by internal heating by radionuclides, specifically aluminum-26. So what is aluminum-26? Aluminum-26 is a short-lived radionuclide with a half-life of about 0.717 million years. This is time after solar system formation. This is the radiogenic heating output, so output in radioactive decay heat in watts per kilogram of chondritic or silicate material of the early solar system. You see that, especially during the disk stage, the heat output from aluminum-26 was several orders of magnitude higher than anything that we know today in the solar system. And this led to large-scale melting of asteroid-like objects, planetesimals, that melted internally and deformed. And this is shown, for instance, in this 3D simulation of the internal deformation of the planetesimal. the colors in this simulation scale with temperature of the body, and you see basically really tailored instabilities developing in the interior of these planetesimals. Now this is important because it means that the formation time of these planetesimal waves is dependent on, or let's say the internal evolution of these planetesimals is dependent on their formation time, because the half-life time of aluminum is so short. And so this is the parameter space of this. This is planetesimal radius. This is formation time after CAIs. And the color scale shows the highest mean temperature. Now, this is important in two aspects, namely water-rock interactions, shown here at the top, and core formation. So basically the buildup of metallic cores in planetesimals and what we measure today as meteorites. So if we bring this back to this initial buildup scenario, you immediately see by matching by eye here these timescales that reservoir 2 planetesimals probably experienced low internal processing. The reservoir 1 planetesimals experienced very high internal processing from the heat output from aluminum-26. And so we asked the question if, using in this build-up scenario, this can explain the chronology that we observe in the meteoritic record. So this plot here quantifies basically the amount of core formation, the separation of metals and silicates in planetesimals that are formed in these reservoirs. This here shows time after CAIs. This is a fraction of birth planetesimal population per reservoir. So basically 100% would be the whole of the planetesimal population in reservoir 1, and in blue 100% would be the whole of reservoir 2. Let's just focus for simplicity actually on this darker peak each time here. This is the change in core formed material, in differentiated material. Basically, when this gives a peak here, this red line here at 1 AU, this tells us that reservoir 1 planetesimals on average experience core formation, separation of metals from silicates at around 1 megayear. And this is because of the heating timescale of aluminum. They form, they heat up, and then they melt, and then metals and silicates can separate due to gravitational separation. Reservoir 2, on the other hand, because it's less processed and less heated from aluminum-26, takes a little bit longer and experiences a peak in core formation about 3 to 4 megayear after CAIs. And this here on the top shows us the timescales of the chronology that we observe in the meteorite record. Red shows the NC reservoir, blue shows the CC reservoir. And you can see that the simulation reproduces these peaks in core formation regimes across so-called magmatic irons in the inner and in the outer solar system. Additionally, actually, these simulations tell us something about aqueous alteration, or the reaction of water with rock in these planetesimal populations. This is shown here, same axis, but this time the peak, these solid lines here, show something else. They show the buildup of hydrous rock phases in aqueously altered planetesimals. So what happens if you have initial water ice rock mixture, like illustrated here? The water ice will start melting and then starts reacting with the ambient rock, forming various phases of phyllosilicates. But at some time, actually, these phyllosilicates will break down again because the temperatures are too high. This is exactly what happens in the inner solar system. Reservoir 1 experiences a very strong peak in hydrothermal activity and forms phyllosilicate phases, which is when this peak develops. But then all of them break down again because the temperatures are so high. Reservoir 2, on the other hand, actually never experienced these high temperatures and therefore actually gets a peak in hydrothermal activity and phyllosilicate formation at about 4 to 5 megayear after CAI, but they remain, they don't break down again. And this explains the difference between the inner solar system, because all these planetesimals here desiccate very strongly, while the outer solar system doesn't, it retains its volatile content. So this is a short summary of this model that is specifically built to explain the chronology and chemical budget deviation between the inner and outer solar system and the accretion timescales. So let me shortly summarize this. Basically gives a physical explanation for the meteoritic chronology in the inner and outer solar system, and predicts that the growth mode of the terrestrial planets switched from initially collisions to then pebbles and then collisions at the very end, because the inner disk was pebble-starved. The solar system dichotomy then is a direct result of distinct bursts of planetesimal formation and the geophysical evolution driven by radiogenic heating, which is the key element that can explain trends in chemical deviation in the inner and the outer solar system. The volatile accretion sequence is a little bit different because of that than in classical models. Basically starts with volatile depleted, desiccated from aluminum-26 heating, then goes over to dry materials, dry pebbles that accrete inside the snow line on the inner terrestrial planetary embryos, and then potentially volatile rich again by scattering. And now, give me just 5 more minutes. I want to come back to this exoplanet question that I actually started to begin with in the first place. Because the chemical deviation in the solar system in this model is a strong function of aluminum-26 heating, this immediately brings the question, what about other planetary systems? How rare, how common is aluminum-26 across planetary systems? And the answer to that is actually, truthfully, we don't know. But this is a very active field of research. And I believe the community in the last few years sort of emerged, or the answer that seems to emerge is that actually aluminum-26 to the levels that the solar system had initially is not a common nor a very rare phenomenon. It's something on the order of a few tens of % of systems have an aluminum-26 initial content like the solar system. The left-hand side just shows a model for me from a few years ago, which is a fraction of planetary systems that are enriched relative to not enriched systems. And this is then the prospective radiogenic heating rate in extrasolar planetesimals relative to the solar system. The solar system is about here. These are different curves and different predictions for different star-forming regions, from low mass to very dense star clusters or star-forming regions. The solar system itself is elevated about 3 to 25 times that of the galactic mean because of uncertainties in how this is measured. And I'd say observationally, in a few papers, you see this number roughly across this number on the order of 25%. Could be as low maybe as 10%, could be as high as 50%, something on that order. There's also evidence that supports this from white dwarf systems. And this is shown in these two plots here. The left-hand side shows the calcium to iron ratio of debris that is accreted onto so-called polluted white dwarfs. And these are white dwarfs are very small stars after basically they burned out from their main sequence phase. And sometimes in some of these white dwarfs, we see evidence for variations in the atmospheres. And this is taken as evidence for accreting asteroids. And some of them look very peculiar. Namely, they are enriched in certain elements. And this is what this plot shows. This is the white dwarf temperatures, not relevant for the point I want to make. But these, specifically these green and these red dots here that are interspersed somewhere here, they give evidence for that these asteroids that are accreted are not just chondritic material, not just the stellar material, but they are structure. They are either cores or the mantles of planetesimals or larger protoplanets. And so there are various ways how this can be done, how these materials that are accreted on these asteroids can be enriched in iron or potentially core material. But several papers, and also this paper that we submitted a few months ago, actually seem to indicate that most of these materials and most of these systems that actually accrete iron-rich material are indeed evidence for planetary material that is differentiated from aluminum-26 heating. And so this pathway here for explaining core mantle-rich material in this system would be the right one, where basically these planetesimals in these polluted white dwarfs originally accreted very rapidly and then differentiated by aluminum-26 heating. And then today we measure the debris of this material in the atmospheres of these white dwarfs. And this indicates that roughly 4 to 66%, which is a large uncertainties because the observations are not that good yet, but the community is obviously working on this, are core mantle-rich fragments. And this is approximately the right uncertainty level for also the predictions for aluminum-26 distribution across exoplanetary systems from star-forming observations and modeling. Okay, this means this is significant actually on the population level. It's neither completely rare nor completely common. And so a few years ago, we asked the question on a exoplanet population level, what does this do with the water content of exoplanetary systems? So what you see here is on the bottom is the planetesimal radius again, that is formed from the streaming instability. This is the aluminum abundance normalized to the solar system value. The streaming instability prefers to form objects on the order of 100 km. You know this type of plot already. The background color is the final planetesimal water content after desiccation by aluminum-26 heating. And so here this upper right edge is dry planetesimals, and this one is wet planetesimals. Now, what we did then in this work was basically we used those desiccation models and inserted them into a planetary formation code that basically calculates the standard planetesimal accretion rates onto planetary embryos. So insert a planetary embryo on the disk, it accretes by planetesimal accretion, migrates in the disk, and then depending on the variation of the initial conditions, it creates basically planetary populations. And this is the result of that exercise. So when you assume that planetesimals start with 50 km planetesimal radii, but the aluminum-26 content is very small, then the resulting exoplanet populations are actually very water-rich. Basically, the typical value of water mass budget in exoplanets and low mass exoplanets. This is a specific plot for all planets below 10 Earth masses and G-type stars, is on the order of 38%, which is approximately water mass content beyond the snow line. If we increase the aluminum-26 content, now unsurprisingly from what I told you before, the median of the distribution of exoplanets generated by that decreases rapidly, up to 1 order of magnitude below the typical value for solar system-like planetary systems, and even further for more highly enriched systems. Now, this comes back to the very beginning, because changes on that level actually change the planetary structure itself, as I said in the very beginning. And so we try to measure that change and try to understand if the upcoming and current transit surveys of exoplanets could measure these changes. And indeed they can. This is shown here on the top left plot. The x-axis shows the predicted mean transit radius deviation of a population of planets that is enriched with aluminum-26 to solar system-like levels compared to a population where there's no aluminum-26. This is the planetary mass, and this line here shows that aluminum-26 enriched systems on average produce smaller planets because they desiccate, they lose their water budget, and they become smaller in total statistically, up to a level where between Mars and Earth-sized planets are up to 10% smaller than in systems that are not enriched. And this is measurable on a population level and will be testable at latest with a Plato mission. Now I want to stop. Let me just shortly explain this diagram here. So these changes actually in our understanding of the chemical budget of extrasolar planets suggest that there are strong deviations across planetary systems. And specifically they highlight that the structure and climate regime of exoplanet is not just an astrophysical, it's not just an astrophysical consideration, but really requires interdisciplinary work across the astrophysical and geophysical domain to understand the diversity of planetary environments in the solar system. So this is illustrated in the diagram here that will come out soon in the PP7 chapter, which basically follows the geophysical evolution of planetary bodies from the planetesimal stage through to this long-term secular geodynamic evolution. Importantly here, and this is the last point I want to make, is that most of that diagram here is actually red. And that is something that we are not used to in our everyday experience, because it means that the planetary mantle is molten in that stage. And this is important because liquid-gas interactions facilitate rapid chemical exchange between subreservoirs, such as the core, the mantle, and the atmosphere. And this is very interesting because these most dramatic changes that planets undergo during the long evolutionary timescales are operating in this very high temperature regime. And this is exactly the regime that we probe at present day with exoplanets, where this diagram here shows planetary mass and installation, various hypothetical climate regimes of exoplanets. And so with the currently probed exoplanetary census, short period exoplanets under high radiation, we're probing planetary climate regimes that were present in the very early solar system, and also the Earth underwent at some stage. So we can use these exoplanets to gain better constraints on high temperature phases. And these in the future will help us to better understand the formation and very early evolution of our own work. And this is actually then a different talk. So let me just put up actually my summary slide, and I'm very happy to take any questions. Thank you.
Okay, thank you very much, Tim. I mean, you know already how it runs, probably most of you, that for asking a question, please either do use the chat function, or you can also switch on your webcam, and then I will give you the word to ask questions. Jan Henrik, please.
Yeah, thank you. It's a very, very interesting talk. I have two probably completely unrelated questions. The first is there a direct way of measuring the aluminum-26 content while it's still high, or are there specific isotopes that you can measure to see whether it once was very high? So can we actually know about the aluminum-26 content?
Do you mean across other planetary systems or in the solar system?
No, across other planetary systems.
Yeah, so we can't, and this is why we have to use indirect evidence. So we can measure it on galactic scales, so using gamma ray observations, and this is basically where the constraints that I mentioned come from. We can measure it in across star forming regions averaged, and those indicate basically the number I mentioned there, that the solar system is somewhat enriched, 3 to 25 times the galactic mean level. But it's not very unusual, but it's enriched to some extent. Now, there's also additional evidence from specifically from isotope ratios in the solar system, for instance, the aluminum-26 to iron-60 ratio, that gives us an idea about actually the enrichment path. And this suggests specifically that it was not a supernova itself that enriched the solar system, but either a Wolf-Rayet star or something different, potentially an AGB star. We cannot probe forming planetary systems directly. Would be great. So if you know a way, find a way to do that, that would be amazing.
I don't. And the other thing is, are there other parameters of your model that would influence the sort of the basic conclusions? I mean, obviously the aluminum-26 concentration is a very important part of the model, but does it depend on other things like size of the disk or mass of
so it depends. The actual so the relative mass budgets of the, maybe I can't come back to that specific slide actually. I don't know. Let's go back to this slide just for illustration purposes. So the different mass budgets of reservoir 1 and reservoir 2, which roughly actually in this scenario reproduce the inner and outer solar system, they are certainly influenced by various parameters. For instance, the rate of turbulence in the disk and rates of coagulation in the disk. The fiducial scenario that is presented here is the amount of, in this specific case, is the most standard value of turbulence that we currently think is what's happening in the mid planes of disks. Yeah, there are various other parameters. There are regimes where this specific mechanism doesn't operate. There are regimes maybe where the so there are a number of parameters, absolutely.
So we might end up observing an exoplanetary system that doesn't behave so nicely, but
absolutely,
if you're having higher radial velocity or something,
it's very easy to get out of this regime ultimately by triggering different scenarios. Yes. I mean, basically what I wanted to say with parts of the talk is that in this scenario you can explain the structure, but across planetary systems we definitely expect a variation of parameters and variable parameters like different disk sizes, different total mass budgets, different coagulation scenarios, and in other inhomogeneities in the disk that will certainly change the outcome of this picture. Yeah, so it's no problem to basically explain variability of exoplanetary systems, but at the same time have this scenario that can give us an indication of how the solar system itself formed.
Yeah, thank you.
Thank you.
Okay. Any other question, please? Flores, please.
Hey Tim, that was great. Thanks very much. I particularly was interested in this in these two groups that you identify in your isotope versus isotope diagram, like the carbon-rich and the carbon-poor groups, and it had measurements, I think, for the Earth, for Mars, and perhaps for the Moon. So that leaves a lot of other planets. Don't we have data for those? Or
you mean this one?
Yeah.
Actually, we don't have any specimen from Venus, nor from Mercury. So no. Getting a specimen from Venus will be first priority. Yes. This is the question, right? Or
I understand that we don't have samples from those planets, but can't we use remote sensing or so?
No, for these epsilon values is one part per 10,000, and only basically the up-to-date mass spectrometers can measure this. You can't do this remotely. You really have to have a sample, put it into a very highly sensitive mass spectrometer, and try to resolve those things. Really, in this type of machines, I'm not a geochemist, I'm not an expert in laboratory measurements, but these types of machines really only became sensitive enough to do this measurement in 2007. Actually, it was the first paper that was able to resolve these differences. So no, we need Hahn samples at the moment to do this. In the very, very distant future, since there have been some claims in the exoplanet community recently that they can distinguish isotopal logs in exoplanetary atmospheres, you can imagine a future where we would be able to resolve isotope difference exoplanetary systems, but by far not on that level. Unfortunately, not. No.
All right. Thank you.
Thank you.
Okay. Any more questions? If not, I would like to thank Tim again for coming, and also you all for attending, and have a nice evening. Goodbye.
Thank you, everyone. Bye.